Okay, we're gonna be going over this. I accidentally forgot to film, so I'm not gonna redo the whole question. I'm just gonna go over the steps. We're going over the Arrow-Pratt measure of absolute risk aversion. As AR increases, your risk aversion increases. So, like it says up there, it's a measure of absolute risk aversion. That's how it's going to look. So it's less your second order condition of the utility function over the first order condition. And I've written some rules here. So alpha equals alpha 1, but it's going to alpha 2, where alpha 2 is greater than alpha 1, and alpha is in between 0 and 1. And your utility function is very easy. It's just x to the power of alpha. So pretty simple stuff. Obviously, it can be used to measure the absolute risk aversion of more complex utilities, but I just wanted to give like a brief something, okay? So there's your first step. This is your second order condition. Second order condition, first order condition, it looks exactly like this, or what it's supposed to look like, and then you just have to solve for it. So it's 1 less alpha x, which makes sense because as alpha increases, your risk aversion is going down. So your AR is going down. And I wrote some, if alpha was 0.5, that's more risk adverse than it being 0.75. And that's in between 0 and 1. So it's following all the rules, but it's not as good as explaining it like this. This is more of like a profound answer than just writing this. So that's why it's more important to use the Arrow-Pratt measure of absolute risk aversion. And it gets really helpful when you're dealing with like very similar risk aversion utilities, and you want to decipher exactly which one is more risk adverse. But there it is. I apologize for not filming every single line, but I don't think this is too complex. So it's a shorter video today.